to avoid collision. The third model is called the linear model. We have mentioned that the previous models are sometimes linear, also linear. But we have no good name to describe this kind of model, so we call it linear model. In this linear model, we are going to see one difference. This acceleration will be a constant multiplied by the speed velocity difference, and plus another constant multiplied by the relative distance, and minus desired falling distance. The only difference here is the falling distance is a function of velocity and acceleration. So they don't have a constant falling distance, but the falling distance is a function of velocity and acceleration. Similarly, this model was calibrated using real data, so they got these constants. This is the third type. The fourth type is called the psychophysical or action point model. In this type of model, they have a good assumption. They assume a driver will perform an action only when it can observe something. So in this psychophysical model, if the driver cannot detect something, it has no reason to react to it. And how can a driver react to something? Then the stimulus or something he observes must exceed a threshold. And there are typically three types of threshold. For example, the visual angle of the vehicle ahead of me should be changing. It should change in the magnitude that I can detect. Otherwise, I won't realize the vehicle ahead of me is changing its relative distance. So we use the visual angle, which is typically delta V divided by the square of delta x. Another possibility is simpler. This threshold is speed difference. If the speed difference is speed difference, I think it's delta V. This should be delta V. Delta x is also, let me check. Sorry, I have to check this. I think delta x and delta v are possibly very similar to each other. So if we, delta x minus time is equal to delta v. But the key here is the threshold is the speed difference. So if the vehicles, I think it's using delta x. This means the driver, if the driver cannot detect any change of their relative position, so if delta x doesn't change, that means delta v doesn't change. So they're very similar. Delta x indicates delta v. If delta x is not changing, that means the delta v is not changing. Correct? Our relative distance doesn't change. That means we have no speed difference. If this changes, it has to exceed a threshold for me to observe it, to detect it. Correct? The third kind of threshold is obtained from experiments. So they only use delta V and delta X, but they conducted few experiments and they obtained some data and they use the data to create other threshold. This is the psychophysical model. The fifth one is called fuzzy logic-based model. Let's take a look at this thing first. This is an explanation of fuzzy logic. In fuzzy logic is based on rules. So you make your decision based on some rules. In a typical rule like this, if the distance is too far, and if our relative speed is closing, which means I'm approaching the vehicle ahead of me, then the driver's response is no action. So this is a rule, simple rule. Let me say again. If the distance is too far, but I'm approaching it, then I do nothing. Now the key of fuzzy logic is how we determine if it's too far or if it's closing. The key of fuzzy fuzzy logic is to fuzzify the variables. Now here's the example. Here's temperature. When temperature is very low, we are 100% sure that it's cold. But when the temperature is higher than another threshold, we say it's definitely not cold. But between these, at a certain point, we say it's like 80% cold or 90% cold. Now, this variable of cold is fuzzified. Similarly, we fuzzify this warm and hot. So if we pick a temperature here, we can say it's like 10% warm and 90% cold. So we don't say it's within this range. We don't say it's cold. We don't say it's not cold. We say it's 90% cold. And based on this, we fuzzy logic can calculate some rules. Can calculate if this condition satisfies any rule. This is a bit hard to understand. I'm introducing it very briefly, but you may want to remember this is the key of fuzzy logic. In other words, it's smoothing. It's essentially smoothing. If we don't have fuzzy logic, we have a variable value here, they suddenly drop to here. So it's not smooth, it's disconnected. With fuzzy logic, we have a smoothing of variables, which is also called fuzzification. But this is only a model that exists in the research. It's not used in any real model. The last one is called the desired spacing model. The desired spacing is a linear function of the speed, and it's an individual driver characteristic. So with different drivers, the desired spacing will be different. And desired spacing is only a function, linear function of the speed. And after that, the desired spacing model only uses the desired spacing as its variable, as its dependent variable. Independent variable. And it's not using reaction time anymore. The reason they eliminated the reaction time is because it was difficult to calibrate the reaction time. And reaction time differs from people to people. As a result, in this kind of model, they try to eliminate this thing to simplify the calibration. But it's not very realistic. At least it's on a track to simplify the model, to fit better to the data. It's not based on how to describe the scenario more realistically. Okay, I have introduced 6 types of car-falling models. Now let's go to the application part. Let's take a look at vSim, Polemics, and Amazon and see how or what kind of models they are using. The first topic is vSim. In vSim, first of all, I want to talk about the 4 driving modes. In vSim, a vehicle at any time point can be one of the 4 driving modes. The first mode is called free driving. So the speed will oscillate around the desired speed. If the desired speed or the speed limit is 50 kilometers per hour, then my speed will oscillate around it. Free driving. The second mode is approaching. In this mode, the driver will start to decelerate because there's a vehicle ahead of me. And I'm approaching to it. And I want the speed difference drop to 0 when I reach the desired safety distance. This is also very reasonable. Do you understand it? I'm approaching you, so I start to decelerate. When I reach the safety distance, our speed difference is 0. The third mode is called following. In this case, the speed, the vehicle and the vehicle ahead of me, my vehicle ahead of me are already having a safety distance. and our speed is almost the same. In this case, the driver, I am driving in the following mode, and the speed difference of the two vehicles are going to oscillate around 0. The last one is called braking. In the braking mode, the drivers are going to hit the brake as hard as possible. This happens when the preceding car changes speed abruptly, or it can also happen when another car changes lane to insert itself between my vehicle and the vehicle ahead of me. These are the cases that a vehicle has to brake hard for driving mode. Now this is a figure that is a bit more difficult to understand, but I want you to focus on this vehicle because it's mentioned a lot of times. This axis is the difference of velocity, delta V. And along this direction, this means the distance is increasing, which also means the vehicle ahead of me is bigger than this means the vehicle ahead of me is traveling faster and faster. Along this direction. And this is the 0 direction, the 0 x or 0 delta V. So at this line, there is no difference. The vehicles are traveling at the same speed. But along this direction, the distance is decreasing. It's decreasing. So this means the vehicle ahead of this vehicle has a faster speed. And this sign means the vehicle ahead of this vehicle is having a slower speed. This is x-axis. Now this axis represents the delta x, which is the distance between those two vehicles. Understand the two axes? Now, if the delta x, the distance is too small, is smaller than the threshold, then there will be collision. So this red region means collision. It's the distance is lower than the safety distance. This is collision.